the 5 steps in executing a RISC instruction. First, fetch it, then decode it, then execute it in the ALU to do, for instance, an add. Then, if the instruction needs, access memory, and if the instruction should write back the result to a register. And these are 5 stages. Other processors can have 20 stages. In that case, for instance, decode is split into several parts. So here we have an example program, and we will see how a pipeline execution can improve the performance of this program. This program doesn't do anything in particular, it's just an illustration. So what we can see here is that this instruction produces a value for R3, and this one does not depend on the value that the previous produced, since it doesn't read R3. So these two are independent. But the add immediate is using the value produced by subtract. So there is a so-called dependence between these two. And the subtract must execute before the add, clearly. Note also that the power subtract instruction is a bit unusual, namely that it's not R7 minus R8, it's R8 minus R7. Okay, that's why it's called subtract from. Okay, and here we also have, here we have a dependence, and there is no dependence, but here is the dependence with R7. Okay, so let's run this in a pipeline. So let's say we have a pipeline, namely a chip with one stage here, and then at the next clock cycle an instruction can move to the next stage to be decoded and then executed, and then, well, here it doesn't do anything, it just goes through without destroying anything, and then it writes back the result to a register. And when the add has come there, the next clock cycle we can start the next instruction, and so on. So it will take 5 clock cycles for each instruction, and in total 10 clock cycles for these two. But what we may want to do is to start the subtract before the add has finished. Actually, we can try to start a new instruction in every clock cycle. What happens then? Well, here we the add is started, and then it is decoded and executed. When the subtract is coming to the decode and wants the operands, well, the operands are still in the register file, so it can just read them, and it continues and executes the instruction in the next clock cycle. When the add immediate has come to the decode, it wants to read the value produced by the subtract. Add immediate uses R6, which is produced by the subtract. Okay, so how can it get it? One way would be to sit here and wait until the subtract has come to this part and written the R6 into, the value into R6. But that's unfortunate. It's a waste of time. So what we can do instead is to, in the hardware design, add a wire so that the result of execute can go back to the decode stage. And then in this decode stage we have like an if statement it's called multiplexer in hardware terminology, and it selects some bits. I mean, it has different alternatives. One alternative is to read the value from the register file. Another alternative is to read the value from here. And actually a third alternative is to read the value from here. Okay, and the condition in this if, so to speak, is whether the register that we want is produced here or there. If it's produced both there and there, which one should we take then? Well, we should take this one because it's the most recent value. So there is some logic which selects input from these three alternatives, and this is this array with registers from R0 to R31. Oops. So okay, and this is done without any performance penalty. Okay, so let's look at the last instruction. It reads R6. No, R7. Well, it reads R6. And where does that come from? When the add, this one wants R6 and R7. When the add wants R6, it can get it from here. Okay, and when it wants R7, it cannot get it from here because the load will have read the value from memory at the next clock cycle when the load is here. So there is nothing the add can do except wait. So in the next clock cycle, the add will still be here, and that one will not exist. And so in the next clock cycle, it can get there and there, etc. This empty slot is called a pipeline stall or pipeline bubble. Okay, so we have a dependence when one instruction produces a value and another reads it. For compilers, it's called dependence, true dependence, and among hardware designers, it's called read after write hazard. Okay, if both instructions write to the same register or memory location, we say it's an output dependence or write after write hazard. And an anti-dependence is an instruction such as this store, which reads R4 and then a subsequent instruction overwrites R4. So these two should not execute in the opposite order. I mean, we must store the value R4 that came from here. Okay, there is actually for compilers another dependence as well. Well, there are several, but well, at least two. For compilers, it's called input dependence. It's when both read the same location, and that doesn't disturb the execution. And then there is control dependence, but that's a different issue. It's when we don't know, well, I can say it, something is control dependent on something else if one instruction determines if the other actually will execute. Okay, so what we have seen is a pipeline stall when an instruction must wait to get the data. And one example is in this pipeline is when we have a load. Okay, and another is a branch, which we didn't see, but when we have a branch and we decide to branch to somewhere else, then we have, well, we can see what happens. If we would have a branch here, branch less than, for instance. Okay, when can we do the branch? Well, not in the fetch, because we don't know yet that it is a branch, and maybe in the decode, but say we don't know yet. Say we decide that we should branch when we are in the execute. Okay, and what has happened is that we have fetched instructions which just happen to be after the branch in memory. So maybe here we fetch the multiply and divide and subtract. Okay, and the multiply. Okay, so if we decide to branch, then maybe we should branch away to somewhere else and not execute the multiply, divide, and subtract. That means these instructions were fetched without being used. So we have wasted these instructions. These fetched instructions are pointless and they will not be executed. So that's the second part of, I mean, a reason for getting pipeline stalls due to branches. Okay, so what can we do about that? Well, we can actually guess whether we should branch or not, and that's what the modern CPUs do. For instance, if we are in a loop, then it's likely that we take one more iteration, and the processor guesses that it should do that and fetches those instructions. So, how can we reduce the effects of pipeline stalls? Here are some that we can avoid as programmers, and some others that the compiler can do. Okay, so we can avoid using global variables in inner loops. And why would that be a good idea? Well, usually global variables, they are not allocated a register, and instead they are fetched from memory. And reading from memory at least takes some clock cycles, and it usually results in a pipeline stall, since there is a load and probably we need that value very soon. Another is avoid using function calls through a pointer. A virtual function is a member function in a class. I mean, not in C, but in C the same problem exists, that we have a pointer to a function and call the function through the pointer. Why is this a problem? Well, if what it means is that it's harder for the processor to guess where to branch, and also for the compiler. So it cannot, for instance, copy and paste the content of a small function. Okay, and also we should avoid having many if and else statements inside inner loops, if we can. Okay, what can compilers do? Well, they can create for each part of well, actually we will come to that at the last lecture, but they can try to rearrange the instructions in order to avoid pipeline stalls. And they can also try to allocate global variables to registers, but that's not so very easy.